Ever wondered what's really going on inside your phone charger? It's not just electronics. The real unsung hero, the hidden force making it all work, is magnetics. So today, let's pull back the curtain on the engineer's secret shortcut for taming this incredible force.
I mean, just look at any power adapter. It's a boring little plastic box, right? But if we could peel back that case, what would we actually find in there? What's the core tech that takes all that power from the wall and safely funnels it into your device? Well, the answer is a tiny, incredibly sophisticated magnetic system. Seriously. Inside that little box, designers are manipulating magnetic fields with amazing precision. And to really get how they pull that off, we have to start with the fundamental laws of the universe itself. All right, so if you want to design these components, you could start from scratch. Go right to the source code of the universe, physics. We're going to call this the hard way. And don't get me wrong, it's powerful, it's fundamental, but as you're about to see, it's not always the most practical way to go for an engineer who's, on a deadline. Okay, so here are the big 3 rules of the game. Rule 1, run an electric current through a wire and you create a magnetic field. Simple enough. Rule 2 is just the reverse. If you have a changing magnetic field, you create a voltage. And finally, there's this simple kind of beautiful rule. Magnetic fields always form closed loops. They don't have a start or an end, they just circle back on themselves. Every single magnetic device in existence has to play by these 3 laws, no exceptions. So, let's put these rules to work. We're going to try to design one of the most basic magnetic components out there, an inductor. This one here is a toroid. That just means it's a donut shape, which is a super common building block in power electronics. Our goal is to figure out its inductance, which is just a fancy way of saying how well does it store energy in a magnetic field.
Using those physics rules, the process is, well, it's a bit of a grind. First, you've got to calculate the raw strength of the magnetic field. Then you figure out the total magnetic flow, which is called flux, inside the core. Next, you have to calculate how that flux is interacting with every single turn of the wire coil. And finally, after all that calculus, you get one number, the inductance, L. It's precise, sure, but wow, is it a lot of work.
But buried deep inside all that heavy math, there's a really fascinating and absolutely critical insight. It's this non-intuitive relationship that every single magnetic designer has to know.
And here it is. The inductance is proportional to the number of turns squared. Think about that. If you double the number of wire loops, you don't just get double the magnetic effect, you quadruple it. Why? Because that coil of wire is doing double duty. It contributes once to creating the field, and then it contributes a second time by interacting with that same field. It's this powerful n-squared effect.
So, this physics-first approach seems to work. We have a formula, we have our cool n-squared rule, but there's a major problem lurking just under the surface here. One that makes this whole method a total nightmare if you're trying to actually manufacture reliable components. The problem is a property called permeability. It's basically how magnetically conductive the core material is, and this property is the enemy. It's just not a stable number. It changes with temperature, it changes with how much power you're pushing through it, and, get this, it can vary by 25% or more from one batch of material to the next. Imagine trying to build millions of identical chargers when your main ingredient is that unstable. You just can't.
And this is where the engineering brilliance really comes in. Instead of wrestling with Maxwell's equations for every single design, engineers developed this elegant analogy, a mental model that simplifies everything by borrowing from a world we're all a lot more familiar with, the simple electrical circuit.
Okay, so check this out, because this is the core aha moment. On the left, you've got your basic electric circuit. Voltage is the push, current is the flow, and resistance is the obstacle. Well, it turns out we can model a magnetic system in the exact same way. We have a magnetic push, a magnetic flow, and a magnetic obstacle. It's a perfect one-to-one mapping.
So, the magnetic push is called magnetomotive force, or MMF. You should think of it exactly like voltage. While voltage pushes electrons, MMF pushes magnetic flux. And you get more of it from having more turns of wire, N, or more current, I. More turns or more current gives you a bigger magnetic push. Simple as that.
The magnetic flow is called flux. This is the stuff that's actually moving through our magnetic pipes. Through the core material, it is the direct equivalent of electrical current flowing through a wire.
And finally, the magnetic obstacle is reluctance. Just like a resistor in an electrical circuit makes it harder for current to flow, Reluctance makes it harder for magnetic flux to flow. So, a material with high permeability, like our iron core, has very low reluctance. It's like a big fat copper wire for magnetism. Now, let's see why this new model is so incredibly powerful. We're going to apply it to a real-world engineering trick, and it's going to reveal a really surprising secret about where energy actually gets stored in these components. Let's go back to our donut-shaped inductor. I make one tiny change. We're going to cut a tiny little gap in the core, filling it with, well, with nothing, just air. Now, this seems completely backward, right? Why would you intentionally break the perfect magnetic path you so carefully built?
And here is the absolutely shocking result. When you do this, almost all of the energy stored in the inductor isn't stored in the expensive magnetic core material. It's stored in that tiny, empty air gap.
But how can that be? How can empty space store more energy than the special magnetic material that was designed for that exact purpose? Well, the answer lies in our new circuit model. Thinking in terms of circuits makes this totally obvious. Air has terrible permeability, which means it has incredibly high reluctance. It's a huge magnetic resistor. The core material, on the other hand, is a great conductor with very low reluctance. Now think about an electric circuit. Where does all the power get dropped? Across the biggest resistor. It's the exact same thing here. Most of the magnetic energy gets concentrated in the highest reluctance part of the circuit, the air gap.
And this is why it is such a brilliant engineering move. Suddenly, your component's performance depends on the physical size of that gap, something you can control with machine precision, not that flaky, unstable core material. This makes the design stable, it lets you store a lot more energy, and it prevents the core from saturating. That's basically it getting magnetically full and just unable to handle any more power. It's a total win-win-win.
So we started this whole journey with a deep dive into the universe's source code, and we ended up with this simple, elegant shortcut. The magnetic circuit model allows engineers to completely bypass all that complex physics and intuitively design the components that power our world. It's a perfect example that great engineering isn't always about solving the hard math. It's about creating a better, simpler model to think with.
So what's the big takeaway here? This journey from complex, messy universal laws to a simple, powerful analogy is a pattern you see everywhere in great engineering. It's all about finding a better way to think. So the next time you plug in your phone, remember the hidden magnetic circuit inside. And then ask yourself, what other parts of our world run on an elegant hidden shortcut?